So this is the second mechanics lecture where we'll be looking at motion graphs and freefall. So the material in this lecture is covered in chapter 2 of the Halliday, Resnick and Walker textbook. So first of all, we'll start with a recap of the most important points from the last lecture. In the last lecture, we saw that vectors can be written with a magnitude and direction or in unit vector notation. So vectors are things which have a magnitude and a direction. Scalars just have a magnitude, though they can be positive or negative depending on the scalar quantity. So vectors can be added head to tail or component by component. Often it's faster to add them component by component. We saw that displacement is given by the change in x, which is the final position minus the initial position. Distance is the total path length, it's a scalar. We saw that the average velocity is given by the displacement divided by the change in time. And we saw that average speed is given by the total distance covered divided by the change in time. So the average speed is a scalar, while the average velocity is a vector. So a direction needs to be given for the average velocity. We saw that the instantaneous velocity is equal to the limit as the time increments go to 0, which we can calculate as dx dt, taking the derivative of the displacement. And it again is a vector. We saw that SI units for distance are meters and for time are seconds. And that it's important to think about how to write down your answers. So you should give your answer with the same number of significant figures as the piece of data used in the calculation with the least number of significant figures. So let's start with our first displacement versus time graph. Now in class we had a look at what it would look like if we modeled this out. So if you look at the mouse pointer now, I'll try and do this for you. So basically for the first second it stays still, and then we travel with a constant velocity in the positive x direction for the next 3 seconds, and then for the next second we go backwards very quickly, and then we start going forward slowly at a constant speed again. So that's what this graph here is telling us. It's telling us about what the distance of the object is along the x-axis with the time. So we can actually calculate the velocity from a distance versus time graph. So the velocity, it turns out, is given by the gradient. So we can calculate the instantaneous velocity at 1 second. Okay, so we want to work out what's the instantaneous velocity at this time, which means exactly how fast is the object traveling at this time. So instantaneous velocity is equal to dx dt. And so that's the gradient of this line. So for 1 second, which is here, we want to calculate the gradient here. So the gradient is just given by the rise, which is going from 0 to 3, divided by the run, and again it's going from 0 to 3. So the gradient is equal to 3 over 3, so that's equal to 1. So here we've got the velocity is equal to 1 meters per second. That's the instantaneous velocity, and it's along the positive x-axis. Then we need to calculate it at 6 seconds. So 6 seconds is here. And here the displacement is not changing. So the rise is actually 0. Divided by the run, we've still got 0. So it's not moving at this point. So the velocity here is equal to 0 meters per second. And then at 8 seconds. So 8 seconds is here. So now we're trying to work out what's the velocity here. So we need to know the gradient for this part. So the gradient for this part is equal to rise over run. Now we're going from 3 up to 10. So the rise is 10 minus 3, and the run we're going from 7 seconds to 10 seconds. So this is 10 minus 7, and so this is equal to 7 over 3 meters per second, which you could work out on a calculator if you wanted. if we do that, we get that this is equal to 2.33 meters per second. And again, this is along the positive x-axis. And now we're asked to calculate the average velocity over the 10-second period. So the average velocity is equal to the change in displacement over the total time. And we are going from 0 meters up to 10 meters. So that's 10. And then the time is over a 10-second time interval, so it's 10. So this is equal to 1 meters per second. And this is along the positive x-axis. Sorry, blocky writing again. Okay, so next we can look at how to calculate acceleration. So acceleration is the rate of change of velocity. So just like with velocity where we had average and instantaneous velocities, we have the same with accelerations. So the average acceleration is equal to the change in the velocity over the entire, divided by the total time period. The instantaneous acceleration, however, is the limit as the time period gets really small, which is just the derivative of the velocity. So this gives us the instantaneous acceleration. So let's continue a bit with this question that we did in the last lecture. We calculated the instantaneous velocity at t equals 0 and at t equals 5. We're considering a particle moving along the x-axis, and we've got its position described here. And remember, it was moving like along a parabola. So this one was following a parabolic path where it was starting at 5 meters. Distance was increasing and then decreasing a bit like this. And we're asked, what is the average acceleration of the particle over the first 5 seconds? So we want our average acceleration, which is equal to delta v over delta t. This is equal to the final velocity minus the initial velocity over the time interval. And we calculated these. So we've got that our final velocity was equal to minus 8 meters per second. Our initial velocity was 2 meters per second, and our time interval was 5 seconds. So this is equal to minus 10 divided by 5. So this is equal to minus 2 meters per second. And then acceleration is a vector as well. So this is the negative, shows that it's going in the negative x direction. So i.e. in negative x direction. Now it says, what is the instantaneous acceleration of the particle at t equals 0 and t equals 5 seconds? So for that, we're going to need to differentiate. So we can get our expression for v because it's dx dt. We did this last time, but I don't have it written here. So we're just differentiating this again. So this is 2 minus 2t. And so a is equal to dv dt, which is the second derivative of this. So when we differentiate this again, we end up with minus 2. And so that tells us that the instantaneous acceleration at 0 and at 5 seconds is minus 2 meters per second. So a at 0 is equal to minus 2 meters per second, and a at 5 seconds is equal to minus 2 meters per second. And so again, this negative shows that it's going in the negative x direction. Okay, so now we're looking at a velocity, that's the velocity on the y-axis, versus time on the x-axis graph. And we're asked which of the following quantities can be obtained from the graph. Part 1, the initial position. Well, the graph doesn't actually tell us anything about where the particle starts from. So we can't actually read this one off the graph, so that's a no. Okay, now the next one is the initial speed. Now remember that speed is the magnitude of the velocity, and this is a velocity time graph. So we can read the initial speed of the graph. Initially, here, it's going at 0 meters per second. So the initial speed is equal to 0. It asks us, can we calculate the initial acceleration? Well, acceleration is related to velocity through dv dt. So acceleration is the gradient of the velocity time graph. We can read off this initial gradient. This is a flat line, so it's a gradient of 0. So the initial acceleration is also 0. Now, can we calculate the total distance traveled? We can, in fact, calculate the total distance traveled. The distance traveled is equal to the area under the graph because the displacement is equal to the integral of the velocity with time. Now, this is asking for distance rather than displacement. So when we're considering displacement, we take the areas on top of the graph as positive and the areas underneath as negative. However, when we're working out the distance, we will want to add these two areas together. So let's work out what these areas are. We can either treat this as a trapezium or we can treat it as a series of triangles and a rectangle. Let's just do the triangles and the rectangles this time. Okay, so this triangle here, we've got a length of 1 and a height of 1, so it's got an area of a half. This rectangle here, length of 2, height of 1, so this has got an area 2. And then we've got this triangle, which has got a length of 2 and a height of 1. So half the breadth times the height gives us 1 in this case. So the area on top is 3.5 meters. So it travels 3.5 meters in the positive direction, and now it's going in the negative direction. So now we work out the area of this triangle here, and we've got a length of 2 and a height of 1. So this one here also has area 1, but it's in the negative direction. So the total distance traveled, we add these together and we get 4.5 meters. To get the total displacement, we're going 3.5 meters in the positive direction and then 1 meter in the negative direction. So we subtract those and we get 2.5 meters in positive direction. And then we're asked, can we calculate the average acceleration? We can calculate the average acceleration because the average acceleration is equal to the final speed minus the initial speed over the time. So the final speed, we can just read that off this graph here. The final speed is velocity. The initial velocity is 0. And then we divide by the total time. We're going from 0 seconds to 8 seconds, so 8. So this is equal to minus 1 over 8 meters per second per second. Now the next thing we're asked to do is for this same graph that we were just considering to draw a displacement versus time graph and an acceleration versus time graph. So let's work on this. Okay, so between 0 and 1 second, the object is not moving. So the displacement is 0, it remains at 0. Now between 1 and 2 seconds, it's getting faster and it's traveling this area here, which we calculated that area and we saw that it was equal to a half. So let's put some numbers here. Let's go 1, 2, 3, because we calculated in the last question that the maximum displacement was 3.5. So these are reasonable numbers here. So between 1 and 2 seconds, it's going faster and faster to get to half. So this is half a meter. So since it's going faster and faster, we'll draw it as a parabola like this, which is curving upwards. Now between 2 and 4 seconds, the velocity is not changing. So if the velocity is not changing, that tells us that the displacement versus time graph is going to have a constant gradient. And we calculated this area as well and found it was 2. So it will end up at 2.5 meters. So that's half a meter plus the extra 2 meters. So at 4 seconds, we want it to get to here and it gets to there using a straight line. That should be a straight line. Sorry, my drawing skills aren't brilliant. Obviously in an exam you'd use a ruler if you were asked to do something like this. Okay, and then this area here we calculated as 1, so it's now slowing down. So we want to get to 3.5 meters, and we get to 3.5 meters at 6 seconds. So this is where we want to get to, but we've got a parabola turning the other way, so it's going slower here. This is less steep, this is more steep. Okay, now between 6 and 8 seconds, it's going in the negative direction. So this tells us that the displacement is decreasing, but it's happening at an increasing rate. So we're going backwards. We worked out this area was 1 as well. So we want to get back to 2.5. So here. So this shape here is a parabola with its peak at 6. So that's what the displacement versus time graph looks like. Now the acceleration is the gradient of the velocity time graph. So just so that we don't get confused, let's switch to blue for the acceleration. So my working to do with acceleration, I can write on in blue. Okay, now between 0 and 1 seconds, the gradient here is 0. So between 0 and 1, we've got no acceleration. Between 1 and 2, we've got a gradient of rise, which is 1, divided by run, which is 1. So between 1 and 2, the acceleration is 1 meter per second. So we'll go like that. Now between 2 and 4, the gradient up here is again 0. So it's not accelerating at that point. So that's 0. And then between 4 and 8, we've got a constant acceleration. So we can work out what this acceleration is using rise. So we've got a rise of 2 and a run of 4. So the acceleration is equal to 2 over 4, which is equal to 0.5 meters per second. So, but that's minus 0.5. So we've got minus 0.5 here, and that's to there. That should be a nice flat line. So that's what our acceleration versus time and our displacement versus time graphs will look like. Okay, so just to highlight a couple of important points, displacement is the area under a velocity versus time graph. And for complex curves, we might need to find this through integration. Acceleration is the gradient of a velocity versus time graph, and this can be found by differentiating the expression. So here's an example problem. The velocity of an object is given by v of t is equal to 5 minus t. The object starts from the position x equals 2, and in part 1, we're asked to sketch a velocity versus time graph for the object for the first 10 seconds of its motion. Okay, so we're just trying to sketch v of t is equal to 5 minus t. So we'll want to put t along here, and we'll want to put v up here. Now, when t is 0, we've got 5 minus 0. So this starts from 5. And at 10 seconds, we've got 5 minus 10. So it ends at minus 5. Now, you can see that this is just a straight line with a gradient minus 1. So that's because v is equal to 5 minus t. And just remember that our equation for a straight line is y is equal to mx plus b. In this case, we've got v along the y-axis. The gradient is the thing in front of the x, but along the x-axis, we've got t. So in front of the x here, we've got minus 1, and then we've got plus 5. So the y-intercept is 5, so we've already noted that when t equals 0, it goes through 5, and the gradient is minus 1. So we can draw this as a straight line. Sorry, it's meant to be a straight line, and it crosses through here. V is equal to 0 when t is equal to 5. So that's at 5 seconds, and this is at 10 seconds, and that's at 0 seconds. So now part 2 asks us to write an expression for the displacement of the object. So the displacement, which we can represent as s or x, is equal to the integral of the velocity with respect to time. So the opposite of differentiating is integrating. So that's what we do to velocity to get the displacement. And so we're integrating 5 minus t dt. And so this is equal to 5t minus t squared on 2. And then when there's no limits on our integral, so we'll end up with a plus c. So what we'll want to do is work out what c is, and to work out what c is, we can use this x is equal to 2 meters at the start. So that tells us when t equals 0, x is equal to 2 meters. And so we can put 2 is equal to 5 times 0 minus 0 squared on 2 plus c, which tells us c is equal to 2. So this tells us that x is equal to 5t minus t squared on 2 plus 2. Now we're asked to sketch an acceleration versus time graph for the object. Okay, so we know that acceleration is equal to dv dt, and so we just need to differentiate our 5 minus t, and that's just equal to minus 1. So this is a nice graph to draw. It's a bit boring. Here's the acceleration, here's the time, here's minus 1, and it's just a straight line like that, always at minus 1. So that's from 0 seconds up to 10 seconds. And then part 4, we're asked to describe in words the motion of this object over 10 seconds. Okay, so looking at the velocity time graph, we can see that the velocity is in the positive direction but decreasing, and then it's in the negative direction. So how we can describe this in words is, well, the object starts at 5 meters. It moves in a positive direction but with a decreasing speed for the next 5 seconds. At 5 seconds, it's at rest and it changes direction. It then speeds up at a steady rate over the next 5 seconds, ending up at a position of minus 5 meters. Okay, so another example problem with an acceleration versus time graph. So we're told that the particle shown in this graph starts from rest at the origin. The first question is, what is the initial velocity? Well, that's really not too hard because the question tells us that it starts from rest. Now, if it starts from rest, that means that the initial velocity is 0. We're then asked to sketch a velocity versus time graph. So let's do that here. Here's velocity, here's time, and we've got 1. Okay, so now we've drawn our axes. Let's sketch this. Between 1 and 3 seconds, the velocity is the area under an acceleration versus time graph. Now, this is a triangle, so the area is half the base times the height. So this is 1.5. And so that tells us that at the end of 3 seconds, the velocity is 1.5 meters per second. And because the acceleration's changing at a constant rate, we've got this gradient here. The velocity versus time graph is going to be a parabola. So that's exactly the same as when we had a velocity time graph and we were drawing the displacement graph. We ended up with a parabola. So here's a parabola. Now between 3 and 5 seconds, it's accelerating at a constant rate. If it's accelerating at a constant rate, that's going to be a straight line on a velocity versus time graph. Now let's calculate how much the velocity changes. How much it changes is equal to the area under the curve here, which is just a rectangle, height 1, width 2, so it's got an area 2. So we are going up to 3.5 meters per second, and we'll do that with a straight line. So this is a straight line. And then between 5 and 6 seconds, the acceleration is decreasing at a constant rate. So we'll have a parabola again. And the change in the velocity is the area under this curve. So this is a triangle with height 1 and width 1. So that's got an area a half. So we're going another half a meter. So we're going up to 4 meters. So at 6, we've got a parabola like this. So this should all join up. And then between 6 and 7 seconds, the acceleration is negative, so it's slowing down. This again has an area a half. So once again, because the acceleration is changing at a steady rate, the velocity versus time graph is a parabola, and it's equal to 0 at 6 seconds. The acceleration 0, so we've got a tangent which is straight at 4 seconds. Now, between 7 and 10 seconds, we've got a negative acceleration, which is constant. The area under this graph here is 3 times 1, so that's 3. And so we're slowing down by 3 meters per second. So we're going from 3.5 down to 0.5. So this point here is at 0.5, and that's a straight line. So straight, and here we've got a parabola, and this is straight, and this is a parabola. Sorry about my drawing skills. Okay, now part 3 says, what is its displacement at t equals 3 seconds? Now this is a little bit hard because we need to calculate the area under this parabola, which we can't really just use geometry to do. So rather than do it that way, we're going to need to integrate it. So let's start with an expression for the acceleration in the first 3 seconds. So just remembering back to when you were learning geometry in school, you had the equation for a straight line was y is equal to mx plus b. So we can apply that to this part of the graph here. So with this part of the graph, hopefully you can see that the y-intercept, b, is equal to 0. That's that point there. Now the gradient, m, is equal to rise over run. The rise, it goes from 0 to 1, so that's 1. And the run, the time goes from 0 to 3, so that's 3 seconds. So the gradient is 1/3. So we've got ax on the y-axis, so we've got ax is equal to m, which is 1/3, times x, which is t, we've got t on the x-axis, plus b, which is plus 0. So this is our expression for the acceleration. Acceleration is equal to t on 3. Now what we're trying to do is get the displacement. So if we get the velocity is equal to the integral of the acceleration with respect to time. So this is equal to the integral of t over 3 dt. So this is equal to t squared over 6 plus c, but we realized that initially it was at rest. So at t equals 0, we've got v equals 0. So this tells us that c is equal to 0. So we've got v is equal to t squared on 6, and we're trying to get the displacement. So to get the displacement, we need to integrate this again. So x is the integral of t squared on 6 dt, which is equal to t cubed over 18 plus c. And we're also told it starts at the origin. So because it starts at the origin, that tells us that x equals 0 when t equals 0, which tells us that c equals 0. And so x is equal to t cubed over 18. Okay, so now we have an expression for how far it has gone in the first 3 seconds. Now we just need to substitute in our time. So x at 3 seconds is equal to 3 cubed over 18. Now I'm going to write 18 as 3 squared times 2, just because that lets me easily see that we've got 3 over 2, which is 1.5 meters. So it goes 1.5 meters in the first 3 seconds. Now it's just a coincidence that this was 1.5. Those don't necessarily have to be the same thing. So then we're asked in part 4, what is the displacement between t equals 3 and t equals 5 seconds? Now this one's a bit easier because we've got our velocity time graph here, and this is a easier shape to figure out. We've got a trapezium here. So for part 4, we can just calculate the area here. So the displacement is equal to, well, the average height. So it's going from 1.5 up to 3.5. So the average height is 2.5. We could do that 1.5 plus 3.5 divided by 2 if we wanted. And then we times it by the width times 2. So this is equal to 5 meters. So the answer to part 4 is 5 meters. So just highlighting a couple of important points. The velocity is the area under an acceleration versus time graph. So we can find this by integrating if it's a complicated kind of shape, but if it's a really simple shape, it can be easier to use geometry to calculate. So to find the displacement from the acceleration, you actually need to integrate twice with respect to time. That's because velocity is the integral of the acceleration, and then displacement is the integral of the velocity. Then if we're going the other way to get from displacement to acceleration, you actually need to differentiate twice. So differentiating once will give you the velocity, and then again to get the acceleration. So to practice this, if you're in 1131, you can try homework set 1, question 3. Okay, so now we're going to start considering free fall. So close to the surface of the Earth, objects experience a constant acceleration, which we give the symbol g, which is due to the gravity of the Earth. Or do they? Okay, so at this point we had a look at a demonstration showing what happened when we dropped two objects. We saw that this is true if we don't have other forces acting like air resistance. So when we can negate the air resistance, then this is absolutely true, and all objects fall at the same rate close to the surface of the Earth, though often in everyday applications there is some air resistance, so it doesn't all behave this ideally. So then just a note, G actually varies a little bit around the Earth. So in Sydney, G is 9.80 meters per second, while the average value for the Earth is 9.81 meters per second. So we'll look at this in more detail later when we study universal gravitation, but it's basically related to how far from the center of the Earth the surface is at that point. So the Earth is not in fact a perfect sphere, though often we model it as one. Okay, so another example, we're asked to draw an acceleration versus velocity and displacement time graph for a ball dropped from a height of 10 meters. And we're told that we can neglect air resistance. So we'll do that in a second. If you want extra practice, then homework set 1, question 1 is a good place to practice. Okay, so I've drawn axes for an acceleration, velocity, and displacement versus time graph. So for the acceleration, we've said that objects accelerate constantly near the surface of the Earth and that the rate is given by g. So here we've got g, which is, well, minus 9.8. And this is constant, so it drops like this until it reaches the surface of the Earth. We won't calculate this time exactly now. We're just looking at the shapes of these graphs. Now, if it's being dropped from rest, then we can assume that the speed is initially 0 and it's accelerating downwards, so it's going to have a negative velocity. Because the acceleration is constant, the velocity is going to be changing constantly, which means it's going to have a constant gradient. So the velocity is going to be a straight line going down like this, and the gradient will be equal to minus g, well, minus 9.8. And displacement, it starts from 10 meters because we're told that it's dropped from a height of 10 meters. And now the velocity is changing at a constant rate. So the displacement graph is actually going to be a parabola. So the gradient of the parabola is 0 when the velocity is 0. So this is going to be a parabola like this. So parabola. And then when the displacement is 0, that's when it reaches the surface of the Earth. So now we're on to the problems at the end of the lecture. So the displacement of an object is described by x is equal to 2t squared minus 3t plus 5. And we're asked to write down an expression for the velocity of the object. So in part 1, we've got x is equal to t squared minus 3t plus 5. And we know that the velocity is equal to dx dt. So we just need to differentiate this. So when we differentiate it, we get 2t minus 3 is the velocity. And then in part 2, we're asked to write down an expression for the acceleration of the object. So the acceleration is the derivative of the velocity, or the second derivative of the displacement. So since we've got the velocity here, we just need to differentiate this. When we differentiate this, we get 2. So this is 2 meters per second per second. And then part 3 asks us to plot graphs showing the displacement versus time, velocity versus time, and acceleration versus time graphs for this object. Okay, so now I've drawn my axes for my displacement, velocity, and acceleration versus time graphs. Okay, so displacement is given by this equation up here. Now we can see that this is a parabola, so it'll be a parabola. We can see that when t equals 0, then we've got x is equal to 0 minus 0 plus 5. So this is going to start from 5. And we can work out where the axis of the parabola are. We could differentiate it and then set the derivative to 0, or we can just use that the axis is minus b over 2a, which is equal to what? 3 over 2, so 1.5. So in this case, because we've got a positive number in front of the t squared, it's a parabola which is going to go like this, curve upwards. Let's work out what the minimum displacement is. That'll be when we put 1.5 into here. So x min is equal to 1.5 squared minus 3 times 1.5 plus 5. And solving that on the calculator, we get 2.75. So here's 2.75. We'll go down there, and then it's a parabola which curves up like this. So getting further and further, faster and faster. Okay, now the velocity, we worked out the equation for the velocity versus time graph here. So at t equals 0, we can see that the velocity is minus 3. And then this is just a straight line graph. We can see that when we can see that it'll go through v equals 0 at t is equal to 1.5, which makes sense because that was where the minimum on our displacement versus time graph was. So this will be 1.5, and then we've just got a nice straight line. So that's as straight as I can draw, trying to go through 1.5. Now the acceleration versus time graph, we've got that our acceleration is constant and it's just equal to 2 meters per second. So we can put 2 there, and this is just a flat line like that. So that solved this problem. Okay, so our next problem. The graph shows the velocity of a car versus time. We're asked, what is the acceleration of the car at t is equal to 30 seconds? Okay, so at 30 seconds, we need to know the acceleration. So we need to know the acceleration here. So in order to do that, we can use that the acceleration is equal to dv dt, which is just equal to the gradient. So we need to work out the gradient of this part of the graph here. So the gradient is equal to the rise. So it's going from 10 up to 30. So we've got the rise is 30 minus 10 over the run. And this is ending at 40 seconds and starting at 20 seconds. So 40 minus 20. So this is equal to 20 over 20, which is equal to 1 meters per second is the acceleration of the cart at this time. Part 2 says, when is the car at rest? Okay, so this part's not too bad. We've got the velocity versus time graph, so it's going to be at rest when the velocity is 0. So we can see that's happening here at this time interval. So it's at rest between 90 and 100 seconds. Part 3 then asks us, how far does the car travel in the 100 seconds shown on the graph? Okay, so for this one, to get how far it's traveled, we need to integrate the velocity. So we need to get the area under the curve. So let's split the curve up into little bits for which it's easy to calculate the area. So between 0 and 20 seconds, we've got a height of 10. So 20 times 10, that's 200, is the distance that it travels. Now between 20 and 40 seconds, this area in here, we have a trapezium. So the area is equal to the average height, which is 10 plus 30 over 2 times the width, which is 20. That's 40 minus 20 to get that 20. And so calculating this, we've got 40 times 10, which is 400. So this area here is 400. Then we've got this rectangle here. This has got a length of 30 and a height of 30. So 30 times 30, that's 900. Now we've got this triangle. It's got a width of 20 and a height of 30. So half the width times the height is 10 times 30, that's 300. And then this one's got 0 area. So to calculate the total distance that it's traveled, we'll just want to add these together. So we've got this is equal to 200 plus 400 plus 900 plus 300, which is equal to 200 plus 400 gives us 600, plus the 900 gives us 1,500, plus the 300 gives us 1,800 meters, or 1.8 kilometers. Part 4 then says, what is the average acceleration of the car over the 100 seconds? So the average acceleration is equal to the final speed minus the initial speed over the total time. These are easy to just read off. So the final speed, finally it's going at 0 meters per second. Initially it's going at 10 meters per second, and this is 100 seconds. So we've got minus 10 divided by 100, which is equal to minus 0.10 meters per second as the average acceleration. Okay, so in this problem, we're told that a ball is dropped from 6 meters. So the initial height is 6 meters in Sydney, where G is equal to 9.80 meters per second. So it's dropping downwards. And we're asked in part 1 to write an expression for the velocity of the ball as a function of time while it falls. So we know that to get the velocity from the acceleration, we need to integrate it. So this is equal to the the integral of g with respect to t. So this is equal to gt plus some constant. Now at t equals 0, we've got that the acceleration is equal to minus 9.80 meters per second. So now if we assume that it's dropped from rest, we know that v equals 0 at t equals 0. So we've got 0 is equal to g times 0 plus c, which tells us that c must be equal to 0. So v is equal to gt, which is equal to minus 9.80 t. So we've put the negative sign there to show that this is a downwards velocity, because the acceleration due to gravity is downwards. Now in part 2, we're asked to write down an expression for the height of the ball. Okay, so we know that the displacement x is the derivative of the velocity with respect to time. So this is equal to the derivative of minus 9.80 t dt, which is equal to minus 4.90 t squared plus c. Now we know that at t equals 0, x is equal to h, because it's dropped from height h, which is 6 meters in this case. So we can substitute these in to find out what our constant of integration is here. So we've got 6 is equal to minus 4.90 times 0 squared plus c, which tells us that c is equal to 6. So we can write, well, the height is equal to minus 4.90 t squared plus 6. Now part 3 asks us how long does it take the ball to reach the ground. So to work that out, it'll reach the ground when the height is 0. So here height equals 0. Up here height is 6 meters. So we just want to set 0 is equal to minus 4.90 t squared plus 6 and solve it to get t. So we have 6 is equal to 4.90 t squared. I move this over to this side and divide it by minus 1. And so t is equal to 6 divided by 4.90, and then we need to take that square root. So solving this, I get 1.10 seconds as the time this ball takes to drop to the ground.